Welcome to the series of lectures on earthquake resistant design of structures. In this course, we'll be talking about the earthquake resistant design of mostly building structures. This is a module 1 where we are going to talk about major earthquakes, their behavior and their occurrence, the response history, and the design spectra of an earthquake. An earthquake is a seismic phenomena that originates below the surface of Earth. The tectonic plates gain strain with convergence, with divergence, and with other motions. The strain is released at a point which is known as hypocenter or focus. The focus is always at a particular depth below the surface of Earth. This depth varies from as less as 10 kilometers to as much as above 300 kilometers. Below 70 kilometer of depth, the earthquake is categorized as shallow earthquake. 70 to 300 kilometer, it's categorized as intermediate earthquake, and above 300 kilometer, it's a deep earthquake. Greater the depth, lesser is the impact of an earthquake. The point which is vertically above the focus, that's known as epicenter. However, if the fault line is visible on the ground, the same point can be described as an epicenter. Now, greater the distance of an epicenter of an earthquake, lesser is the impact on the structure. Whenever an earthquake occurs, there is always a large scale of damage or to structures, be it roads, buildings, dams, etc. There have been major earthquakes in the world over age and centuries. In each of these earthquakes, the death toll has been in tens of thousands. Such large earthquakes have periodically changed the course of history. In recent years, large earthquakes have been coming at regular intervals. One may have a look at the 2010 Haiti earthquake, which was quite devastating and led to a varying death toll from 46,000 to 3,16,000. A 2004 Indo-Indian Ocean earthquake in Indonesia and Sumatra, which had a death toll of 2,27,898. 1976 Hebei, China earthquake with the death toll varying from 2,42,769 to 7 lakh. A 1923 Kanto, Japan earthquake with a death toll of 1,05385. 1920 China earthquake with a death toll of 2,73400. 1556 Shanxi, China earthquake with a death toll of 8,20,000 to 8,30,000, and a way back centuries old 1138 Syria earthquake with a death toll of 1,30,000 to 2,30,000. Each of these earthquakes has been a devastating earthquake and has been recorded in history books to be the major impacting factor in the world's history. There have been major earthquakes in India as well. The recent 2005 Kashmir earthquake, which measured 7.6 on the Richter scale and led to deaths of 86,000 to 87,000 people and injuries equally to 69,000 to 75,000 people, displacing millions. Around 2.8 million people were displaced. There was another Gujarat earthquake in 2001 with a magnitude of 7.7 on the Richter scale, and it led to the deaths of 13,805 to 20,023, varying figures, and injuries to around 1,66,800. Then there was a Latur earthquake of 1993 with a magnitude of 6.2 on the Richter scale and deaths of 9,748. injuries to 30,000. 1991 Uttarkashi earthquake, magnitude of 6.8, deaths 768 to 2000 reported, and injuries to 1383 to 1800. A 1950 Assam earthquake with a magnitude of 8.6 on the Richter scale, 1600 to 3300 deaths reported. 1905 Kangra earthquake, which was measured 7.8 on the Richter scale, with deaths greater than 20,000. An 1885 Srinagar, Kashmir earthquake, with deaths reported to be around 3,000. The theory of earthquakes is the scientific theory of seven large plates and the movements of large number of smaller plates. Since the tectonic processes began 3.3 to 3.5 billion years ago, a theory of continental drift followed by plate tectonic theory, which was accepted in 1950s and 1960s. It's the upper layer of the planet, the lithosphere, that is in constant motion, being drift divided into tectonic plates. On a 0 mm to 100 mm movement of plates leads to earthquakes, volcanic activity, mountain building, and ocean trenches. Although these theories and their processes are incompletely defined, one is not able to predict earthquakes accurately, exactly, and precisely. Thus arises the need for studying the subject. Now, how do we measure earthquakes? This is quite important for a structural engineer. An axillograph, which is a strong motion instrument, it's also known by seismograph. It's commonly self-contained in a box, and it records on a paper or in a digital mode. The data, once in a digital mode, is then available on the internet. An axillograph measures acceleration with respect to time, number one. Number two, it for the record, it also determines p ground acceleration. So we can compute the p ground acceleration from the axillograph. Then we can determine the p ground velocity, and finally we can determine the p ground displacement. Moreover, a response spectrum can also be computed to show how an earthquake affects the structure of different natural frequencies or periods. Then these observations would be useful to the study of the seismic hazard of a particular area. An axillograph has a transducer which measures the strong ground motions. It has a frequency of 25 Hz for modern analog instruments and a viscous damping of 60%. For modern digital axillographs, the frequency is about 50 Hz and the viscous damping is around 70%. Let's first concentrate on the acceleration time histories. Herein are given the acceleration time graphs of two strong shakings. One is an El Centro earthquake of 1940 and the other is a Chile earthquake of 1985. The ground motion clearly varies with time irregularly. The ground motion of El Centro earthquake is 32 to 35% of 1g, which is 9.81 meter per second square, and of the Chile earthquake is 50 to 65% of 1g. The peak duration of El Centro earthquake is 32 to 54 seconds, and of Chile earthquake is 60 to 80 seconds. So when a particular acceleration time graph is applied on a structure, the structure sets in motion. Given a rigid base, the ground motions are transferred to the structure. We know that the acceleration time graph is highly irregular. Despite that, ground motion is considered known even when acceleration time graph is irregular. So during earthquake, displacement type loading on structure, wherein structure undergoes displacement from the initial position, occurs. This displacement leads to the development of stresses in building, and these stresses in the building are cyclic. Equations of motion of a structure under ground acceleration would be given as given here. Acceleration of the ground here is ug double dot t, and u is the displacement of a structure, u dot is the velocity of the structure, u double dot is the acceleration of the structure. Acceleration of a structure is important as it gives us the acceleration of sensitive equipments which may be placed within the structure. Velocity of a structure helps in determination of acceleration of a structure, and displacement of a structure gives us an idea of the amount of distance required between structures to avoid pounding. All these three are known as response quantities. Now, deformation ut is dependent on the time period of the structure Tn and on the damping of the structure zeta. This is known from the dynamics of structures. Let us take the example of El Centro earthquake, where from we have the acceleration time graph. Upon numerical analysis of equation of motion that's known to us, which is mu double dot plus cu dot plus ku is equal to minus mu double dot gt. As we have earlier shown, we get deformation u which is varying with respect to time t. If damping is kept constant at 2% and the time period is varied first from 0.5 seconds, then to 1 second, and finally to 2 seconds, what we get is a deformation time curve, which is also known as deformation time response history, because it's the response of the structure. It can be seen that the longer the vibration cycle, greater is the amount of deformation obtained for a structure. Similarly, when the time period is kept at 2 seconds and the damping is varied from 0% to 5% for the structure, a deformation time history, time response history was obtained, which is seen here. It was seen that greater the damping, lesser are the deformation responses of the structure. Note that the numerical analysis was performed in order to determine these deformation response histories. Now this is known as deformation response history. Next comes the determination of static forces from deformation time response history. For a completely rigid system, one can say that the response of inertial mass of a structure is m into agt, where ag is equal to ug double dot. However, otherwise for systems with certain stiffness of columns, an equivalent static system has Fs equal to k into ut. We have k is equal to m into omega square, thereby which implies Fs is equal to m omega square into ut, which further implies Fs is equal to m into a, where a is equal to omega square into ut. This is easy to determine as ut is the deformation time response history, which is known after determining from acceleration time history. Thereby Fs is equal to m into a is easy to determine. Now here a is the pseudo acceleration. Moreover, considering no additional forces, a static equilibrium would mean Fs is equal to Vb, where Vb is the base shear force. Further, moment Mb at the base of the structure would be Mb equal to Vb into h. Now VB into H is equal to Fs into H. Thereby Fs, which is equal to Vb, and Mb, which is in the moment at the base, are both the static forces. Now, after determining these static forces, one can resolve the structure statically at various time intervals. Next, we are going to determine the response spectrum. The peak of the deformation ut is u naught t or u max t for a given time period and damping. We have already determined the deformation response and the relationship between the peak of ut with respect to time period of the structure, that is known as deformation response spectrum. What is a response spectrum? Response spectrum is the spectra of peak of response quantities with respect to time period. What were the response quantities that we had determined up till now? One was deformation, other was velocity, and third one was acceleration. Deformation response spectrum can be obtained from earlier computation of deformation response history. The peak of deformation response history for constant damping of 2% that was obtained earlier. What were the values? The values that were obtained for a single degree freedom system was 2.67 inch at time period of 0.5, 5.97 inch at time period of 1 second, and 7.47 inch at time period of 2 seconds. Thereby, a deformation response spectrum is plotted here in the figure. Next, we come to the pseudo velocity response spectrum. Now, what is the pseudo velocity? Pseudo velocity V is equal to omega into ut. Now, once the pseudo velocity, the peak of the pseudo velocity is plotted with respect to the time period Tn for a given constant damping, we get a pseudo velocity response spectrum as given in the figure here. Pseudo acceleration response spectrum is obtained from A equal to omega square ut that we had obtained earlier. Now, once the peak of A is plotted with respect to various time periods, what we get is a pseudo acceleration response spectrum as given in the figure here. Next, a combined logarithmic DVA response spectrum is plotted. Now, what is a DVA response spectrum? It was given by N.M. Newmark in 1960, and in this four-way logarithmic plot is plotted. In a four-way logarithmic plot, the values of D and A are both at right angles to each other, while as both of them are at 45 degree to the value of V. Now, we are already aware that D is the peak of the deformation response history. A is the peak of the pseudo acceleration response history, and V is the peak of the pseudo velocity response history. Now, once these are plotted, it could be represented by a single line that is being here plotted for zeta equal to 0.02. So we could obtain for any given point the value of D, A and V from this curve. Now, why is the deformation spectrum important? The deformation spectrum is important because it provides us the peak deformation. Similarly, the acceleration spectrum is important because it provides us the base shear of the structure once under an earthquake. The velocity spectrum provides us the peak strain energy during an earthquake. Now, given that we have developed a DVA spectrum, it is quite feasible to determine all the other identified response quantities and the base shear, the moments, and many other parameters. Finally, in this lecture, we would be discussing the development of the response spectrum. The first step in the development of the response spectrum is to define the ground acceleration UG double dot at any particular instant of time. Now, the ground accelerations are determined at every 0.02 second time interval so that we have a numerical values of ground acceleration for every 0.02 second of time interval. Second step is that the natural time period is selected Tn, and the damping constant zeta is also selected. Now, for given this time period Tn and damping constant zeta, in the third step the deformation response Ut is computed for the structure, and we have already discussed this, how deformation response is determined. In the fourth step, the peak value of Ut is determined, and that value is U0 t. Now, this peak value will be for a particular time period and for a particular damping ratio. In the fifth step, once we know the values of U0 for a particular Tn, we can determine the value of peak deformation, that's D, peak velocity, that's pseudo velocity, that's V, and peak pseudo acceleration, that's A. We know that V is equal to omega into D and A is equal to omega square into D. In the sixth step, all the values of D, V and A are now determined for different time periods and for different values of zeta. Thereby, we can determine the graph for the response spectrum from the peak values of D, V and A for different time periods, and for a particular curve will be valid for a constant value of zeta. So there will be number of curves for different values of damping.